We are discussing chemical bonding, and in the last session, I just wanted to brief you, and I wanted to always brief you at the start of the session that a bond is basically a force, right? Don't imagine anything other than force. It can be stories, but I think you must be focusing on the force because the bond is nothing but a force. When you say force, I think force will be several types. It can be an induced force, it can be an electrostatic force, the most convincing one, and you have a covalent force and you have a metallic force. Since you are assuming a bond to be a force, then you can have several types of bonds, several types of forces. The first one we were discussing about ionic compounds, and ionic compounds are basically made up of ions. They have definite shapes. The shapes have been understood. The lattices have been discussed. The unit cells have been discussed. The face-centered cubes, the body-centered cubes, etc. Now, when coming to the chemical bonding, I face an issue rather. And I was always telling you it's most convincing is the ionic bond, because you have oppositely charged ions, and having a natural electrostatic force seems to be absolutely natural, and by default we are convincing that the strength of the bond is actually derived from the electrostatic force which is actually binding these two ions together, right? So it's so convincing. But coming to the chemical bonding, we always were telling about a narrative being built that people don't achieve octets, so what they do is they share their pair of electrons, and then they share and they get each atom achieve their octet, hence the bond. Well, fine, that's a good way of describing covalent bond. But the issue arises, where does the strength of the covalent bond come from? That is a basic question one must ask, right? You might tell that, people have achieving octet, wanted to achieve octet. So you give one, I give one, both pair will be put it at the center, and we count in both the accounts, and both we will actually achieve what? The octet. That's fine. But the issue is, I'm not convinced at all. How the strength of the covalent bond has been derived from. The strength of the covalent bond is derived from what? Right? You can't explain just by telling that you share electrons a bond pair to achieve octet. And all this is fine, but where is the strength is attained from in case of what? Covalent bonding. And the best example and the best way to explain where does the strength come from in covalent bond is, first of all, introduce the concept of what? Overlapping. You must be introducing the concept of what? Overlapping, you must understand, right? So you must introduce the concept of overlapping, and I have done it, and this is Linus Pauling has done it. Right? And what he says is, during the concept, when atomic orbitals overlap, then the orbitals are delocalizing over a larger volume. So the atoms, I can call the electrons to be localized ones, and when the atomic orbitals overlap, and when you introduce the concept of overlapping, then the molecular orbital is much bigger in size, and the electrons are now revolving, are rotating, are roaming around a larger volume. Thereby they emit energy, lose energy, and gain stability, and that's where the strength of the covalent bond is attained. So this is the explanation what Linus Pauling has to give. And let me tell you first of all that the Linus Pauling theory, which I call this to be a valence bond theory, which introduces the concept of overlapping for the first time, well, it prevails right now. You might be proposing n number of theories coming in chemical bonding, but I think the concept of overlapping is the great thing because it explains from where the strength of the covalent bond is derived from, right? So you must understand this, right? So you might be having some great merits for what? Linus Pauling and the valence bond theory. And I was telling you that the biggest merits is if anyone can explain beautifully the molecules of hydrogen and chlorine and fluorine and oxygen and nitrogen and HCl or HF. Look into this. There is something common in all this. There is absolutely something common in all this. Look into this. The number of atoms are 2. Number of atoms are 2, 2, 2, 2, 2, 2, and 2. So basically, this entire focus of valence bond theory is on diatomic molecules. And I would like to claim that if anyone has explained to his best, the structures of what? The diatomic molecules, it would be Linus Pauling and the valence bond theory. But I wanted to ask you, we are not having only diatomic molecules in chemistry. You have polyatomic molecules, you have ammonia, you have NH3, you have H2O, you have CH4, you have C2H4, and so many other molecules. if you just hang on to just diatomic molecules, you won't be covering even 0.01% of the molecules that are available outside. Right? But what to do? The concept of overlapping has been introduced to tell people that the covalent bond strength is derived because of the interaction of the concept of overlapping. Because what happens is a delocalization is taking place. When you overlap, you get to roam around a larger volume. When you get to roam around a larger volume, more energy is released. Then I think the stability is achieved. You must understand, because stability and energy are inversely related. You must understand that, right? And on the top, valence bond theory has its own limitations, and it is only applicable for diatomic molecules. And if anyone is beautifully explaining the structures of the molecules which are on the board here, then the credit would go toward, of course, what Linus Pauling. But as I told you, you just can't hang on to diatomic molecules. You have several other polyatomic molecules, right? For example, you have all these. You have beryllium chloride, you have beryllium fluoride, you have ammonia, you have PH3, you have water, you have H2S, you have H2T, you have all these polyatomic molecules, which Linus Pauling in his valence bond theory not only fails but miserably fails. That is the issue. That is the basic issue. Right? Well, one greatest merit of valence bond theory is the introduction of the concept of overlapping. That will be carried forward for the further theories also. But if you ask me what is the biggest demerit of valence bond theory of the Linus Pauling, is basically he is limited only to explain the structures of what these diatomic molecules, but he not only fails but miserably fails in explaining the structures of what the polyatomic molecules. If you ask me why, look into this, that when diatomic molecules, you don't need to discuss a bond angle, right? If you wanted an angle, it should be 3 atoms minimum, right? 3 atoms minimum, like angle ABC. You cannot have an angle between A and B, right? So in diatomic molecules, one headache is removed for Linus Pauling. That is, he need not discuss anything about what? The bond angles. But if you come to polyatomic molecules or the triatomic molecules or whatever you hear, I think you must be discussing even the bond angles. The angle between 2 bonds. You must be discussing what is the angle of beryllium chloride is 180. What is a bond angle in beryllium fluoride? It is 180. It's ammonia, it's 107. In PH3, it is pyramidal, that is again 106. And then you have water 104. H2S is angular, 92. H2T is 90. Now, is there any way to basically explain all these bond angles in these polyatomic molecules? This is the issue. That is the basic issue. You must understand that, right? So, yes, you have merits, you have demerits. In fact, everyone will be having merits or not, I don't know, but everyone will be having demerits, and we need to take forward taking the demerits into consideration and move on to the next theory. But before I actually move on to the next theory, I would like to tell you where the Linus Pauling basically fails in treating the polyatomic molecules, right? Let us take an example and explain how he miserably fails in explaining what the polyatomic molecules and their bond angles and their structures, right? Before I go there, and let me tell you that the biggest merit of the Linus Pauling's valence bond theory, if someone is asking you when you venture out, right? The biggest merit is basically introduction of the concept of overlapping itself, right? And it is not the atoms that are overlapping. It's not the atoms as a whole are overlapping. It is only a small orbitals in which the electrons possess opposite spin. They overlap, and then they catch this atom and catch this atom together, and that is how the bond is established. You must understand. When this theory was not prevailing, then people were thinking that the atoms are overlapping on one another. No, it's not hydrogen atom versus hydrogen atom here. It's not chlorine atom versus chlorine atom. And let me tell you that chlorine is so big, one atom is not overlapping with the other to form a bond, right? It is only the 3p-Z electron in chlorine and the 3p-Z electron in another chlorine, which are actually overlapping head-on, and it's carrying this chlorine and this chlorine together, and the bond is actually formed. You must understand that. It's no atoms overlapping, it's basically a chemical bond is formed by overlapping of atomic orbitals. So the concept of overlapping is the best merit of Linus Pauling because it gives us an idea where does the strength of the covalent bond is derived, because it is easy for explaining the strength of the ionic bond. It's difficult for us to actually explain the strength of the covalent bond unless we introduce the concept of overlapping, which is done by Linus Pauling, right? Now, where does he miserably fail? Look into this. Let me take examples, right? Watch carefully here. I take an example. Look into this. This I call them to be demerits. Demerits of valence bond theory. And this might be a question in exam. This might be a question in exam. Demerits of valence bond theory. Now what happens is, this is what is the issue basically. Everywhere in chemistry, he cannot explain this. He is not in a position to explain this. I did ask him, can he explain? Well, he is not in a position to explain, hence I am actually discussing under drawbacks, right? So what is that we put into explain is projection of p orbital. I call this to be p orbital because it has a direction. So I call this to be a vector. P orbital vector onto S is not fixed. Well, that is a terminology what I'm using. It's easy, don't get threatened because it is as simple as that. The projection means the overlapping. The projection is basically the overlapping of a p orbital or a p orbital vector onto an s orbital is absolutely not fixed. When the overlapping is not fixed, the bond angle is not fixed. When the bond angle is not fixed, you are not in a position to tell the shape of what? That particular molecule. That is the issue. Basically, that is the issue. So, if someone is asking what is the biggest drawback of valence bond theory and Linus Pauling, it will be projection of p orbital onto S is absolutely not fixed. When the projection is not fixed, then I would like to say, then bond angle is not fixed. When the bond angle is not fixed, then the shape cannot be determined. Shape not determined. You must understand this. So one of the biggest demerits of valence bond theory is the projection of a p vector onto S is absolutely not fixed. Now what do you mean by that? For example, it is like this. This is the S orbital which is spherical. It's spherical. And you have a p orbital. It's coming this way, right? That's coming that way. And that's not fixed. That's not fixed. It can come acute. It can come this way, further acute, perpendicular, obtuse. You must understand. So whether it's coming acute, very acute, or perpendicular, or even beyond the perpendicular, there is obtuse. In which direction a p orbital projects onto S is absolutely not fixed. It's so random in nature. If you say acute, the one angle must be acute. If you say perpendicular, it must be 90. If it is greater than that, it's 100, 120, 130, 180. The bond angle is absolutely cannot be fixed. The projection of P onto S is absolutely no fixture. Inward, the valence bond theory proposed by Linus Pauling. That is the major issue with this theory. You must understand. That is the biggest issue with this theory. No one has told that you come obtuse, right? No one has told that you come acute. No one is told that you come perpendicular. So this direction of the P vector onto the S is absolutely not fixed. Well, I can be specific by taking an example for this. Well, let us see where the P vector onto S is absolutely not fixed. And I take an example for you. Observe carefully. Well, if this is the case, let us take an example of this. Projection of P onto S not fixed, right? And the best example is beryllium chloride, and that is BeCl2. Let's take the example of beryllium chloride and explain that the projection of P onto S is absolutely not fixed, right? Let us take the example. Now look into this. You have one beryllium and two chlorine atoms in beryllium chloride, right? So if I can write the beryllium configuration, it is 4. Beryllium configuration is 4, and the configuration is basically 1s2, 2s2, and the entire 2p is vacant, 2p is 0, 2py0, 2pz0. And I was always telling you I have the habit of underlining the outermost shell. And the outermost shell is nothing but the number. And if you look into the outermost number, it is basically 2. So I underline all this. That is the ground state configuration of chlorine. You can see the 4 electrons, and I'm showing symbolically you don't have electrons, but I say the entire 2p subshell is basically what? Vacant. The second subshell. Right? And if this is the case, now as I said, this is beryllium, and the 2 chlorine atoms are very much interested to have a bond between what? Beryllium, or beryllium is interested to have a bond between with chlorines. So what is being done is the chlorine atoms are approaching beryllium. These chlorine atoms are approaching beryllium to have a bond. And they are coming. When you come to approach beryllium, they are vomiting energy. And they are vomiting energy because movement from one place to the other, you will have loss of energy. So in the guise of participating in bonding, these chlorine atoms are approaching what? Beryllium. And when they are approaching, energy is lost. Basically, the energy is lost. This lost energy is basically absorbed by beryllium. So the vomited energy, the quantity of the vomit is basically absorbed by beryllium, which is otherwise in the ground state. So this vomited energy is eaten away by beryllium. When you eat away the beryllium, we were told in sciences, in atomic structure, I was studying the quantum mechanics, in which people told that absorption or emission of energy by bodies is always done in form of quanta, packets, right? So if I emit energy, this is absorbed by another body in terms of packets. So it can be 1 packet, 1 quanta, 2 quanta, 3 quanta, 4 quanta, but it cannot be half quanta or 3 by 4 quanta. It cannot be what? Fractional, you must understand. Right? So it is now the chlorine atoms are approaching the beryllium, and when they are approaching the beryllium, they are vomiting energy. When they vomit energy, this vomit quantity is taken by what? The beryllium and rises to excited state. And the quanta is given by h nu, right? The amount of quantity eaten away is given by h nu. 1 h nu is 1 quanta, 2 h nu is 2 quanta, because the energy is quantized, right? So this beryllium, which is there in the ground state, which is 4, which is having this configuration, is now eating some energy, nh nu. Let us say it has eaten away nh nu, and this energy is vomited by the chlorine atoms. That is a vomit by chlorine atoms, and it is eaten away 2h nu, 3h nu, or whatever. Let's put it to be nh nu. But if in the ground state, if you're eating some energy, you basically rise to an excited state, right? So I'm very smart. If someone is asking me, what is the difference between a ground state atom and an excited state atom? Then basically it is nothing but what? A quantum of energy. So I can simply say the GS, that is ground state atom, and the excited state atom, what is the difference? It is h nu. It's simply a quantum of energy. And the quantum is what? The energy content in the packet, that is h nu. The difference between the GS and the excited state is h nu, right? So, these chlorine atoms are approaching the beryllium, and they have vomited that energy, and the beryllium is eating away the energy in terms of packets. That's what quantized, and it is nh nu. It has eaten. Then when you get into excited state, this I call the excited state of beryllium. The excited state. What is happening is, in excited state, the paired electrons become unpaired, because it is only in chemistry the unpaired get paired. Not everyone are involved in bonding. It's only the unpaired electrons get what? Paired. Since you are in excited state, you kick one of the electrons from S to P. So the configuration looks like this. It's 1s2, it's 2s1 and 2px1, and this is 2py0, 2pz0. Now you can see that in the excited state you have two unpaired electrons. You basically have two unpaired electrons. In the first case, in the ground state, you can actually see that you don't have unpaired electrons. So you need to first get into the excited state. For getting into excited state, you should eat energy. When you have eaten energy, you rise to excited state and the paired electrons are kicked as unpaired electrons, right? They have come into an unpaired electrons, and now what happens? If I can write the chlorine configurations which are approaching the beryllium. It is the chlorine which is approaching the beryllium, and look into the unpaired electrons in chlorine. It is 17, so it is 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, and 3pz1. Look into this unpaired electron which is over here. You must understand, here is an unpaired electron. Now this unpaired electron will be overlapping with the unpaired electrons of what? Beryllium. That's valence bond theory. That is a valence bond theory. You must understand. So if I can put it properly here, watch carefully here. Beryllium chloride, in beryllium chloride, beryllium is having unpaired electrons in the 2s and the 2p. You have one electron here, right? And the chlorine is having an unpaired electron. The chlorine is having an unpaired electron in 3pz, right? And now you have two chlorine atoms. So one of the chlorine atoms will go and have a head-on overlap with this. This is head-on. That's head-on. So what is the issue? There is absolutely no issue. Well, P and P overlapping is no issue at all. This is absolutely no issue. This 2p of beryllium and the 3p of chlorine overlap and you get a bond. So that is basically not an issue at all. This is no issue at all. The P projection onto P is never an issue. Don't forget what we are discussing. We are discussing the projection of P onto S. So in beryllium you have unpaired electrons in S and P, and one of the chlorine is coming and getting the P electrons and now projecting onto P. P onto P is not an issue. P onto P is no issue. The issue is only P with S. So one more chlorine comes, right? It also has 3pz, and this 3p now projecting onto S becomes an issue. This P onto this S is an issue. Projection of P onto S becomes an issue. It becomes an issue. Well, what I will do, I will map this entire discussion in one single diagram. Let us map everything in one single diagram. Right? Before I rub all this and map it on one single diagram, well, I wanted to tell you what we are discussing is basically the demerits of what? Valence bond theory, which we were proud of. We must be proud of certain things. Of course, the concept of overlapping, which tells you where the strength of the covalent bond is derived. The second thing is the biggest merits is no one can ever explain so beautifully explained the diatomic molecule structures. But at the same time, this fellow has demerits. One of the biggest demerits is the projection of P onto S is absolutely not fixed. The projection of a P vector onto S is absolutely not fixed. Then it's not fixed, bond angle not fixed, bond angle not fixed, shape is not determined. So for all the polyatomic molecules, he faces an issue, right? The projection can be acute, perpendicular, or obtuse, or whatever, which way he is not telling us. This we encountered by taking an example of beryllium chloride. In beryllium, you have unpaired electrons in the excited state, that is in 2s and 2p, right? And the chlorine is coming with an unpaired electron from the p orbital. So P onto P is no issue, the P onto S is an issue. The P onto S is an issue, right? So what we will do is basically map it off everything in one diagram. Let us say and map it off in one diagram. Let us say this. Watch. So what we will do is we'll map this entire thing in one single diagram for a better understanding, right? Look into this, right? One of the biggest demerits is P vector onto S, not fixed. And then I am showing it in beryllium chloride. The beryllium will have 2s, you have 1 electron, and the 2p, you have 1 electron. And one chlorine will be having in 3pZ 1 electron, and the other chlorine will be having in 3pZ. Right? So let's put everything in one single diagram for better understanding. The only issue we will encounter is only when P with S. Others all are fine. For example, say this. This is the S of beryllium. This is the P of beryllium. This is the S of beryllium, and this is the P of beryllium, both together. The S and P both together, right? And now you have one of the p orbitals coming and overlapping with this. This is a p-p head-on, and you form a sigma bond. And this is nothing but the 3p jet of chlorine. That is the 3p jet of chlorine, and it's non-issue. There is no issue in this. There is absolutely no issue in this. We face an issue with the p vector onto S. This pp overlapping is never an issue. So, one of the chlorine overlapping with this is not a problem. Not a problem. But the other P onto S is a major issue. Look at this. Look into this. This one onto this. If I can draw, now look here. This is the 3p jet of another chlorine atom. Of another chlorine. Now this direction can be this way, this way, this way, or perpendicular, or obtuse, or obtuse, or obtuse, or whatever. This direction of the P onto S is not fixed. The P onto the S is absolutely not fixed. When the P onto S is not fixed, I need to check a bond angle. This will be the bond angle. The angle between two bonded orbitals. Is it obtuse? Is it perpendicular? Is it obtuse? Or it's linear? Is the issue. It's not fixed. It's not fixed. Right? But remember that I am not determining bond angles here. See, you should understand the perception over here. I am not determining any bond angles here. The beryllium molecule, beryllium chloride molecule is formed. It is already there in the laboratory. It is already there. The bond angle is also there. People know it. The only thing is you should explain through a theory to correspond to that bond angle and to correspond to the structure which is already formed in the lab. If that is the case, then remember the beryllium chloride, this is the beryllium chloride, the bond angle is 180. It is 180 degrees. But this cannot be explained because this way it is coming, or this way it's coming, this way, or it's linear. The way the P projection onto S is absolutely not fixed. When the P projection onto S is not fixed, then the bond angle cannot be explained and it's not fixed. And the bond angle is not explained, then the shape of the molecule is absolutely not fixed. This becomes an issue, and the valence bond theory cannot explain beryllium chloride's bond angle. Not only beryllium chloride's bond angle, we cannot restrict to this particular discussion, but as a matured guy, you must understand that the projection of the P vector onto S is not fixed. It's not fixed. So if I can redraw this for you, if I can redraw this for you, if I can redraw this for you for better understanding, it is like this. This is the S of beryllium. This is the P of beryllium. So this is S of beryllium and this is the P of beryllium. And this is the chlorine p orbital. This is the p of chlorine. And this is basically head-on. Sigma, no issue. But the other p of chlorine, this is the p of chlorine, is coming this way, or you come this way, or you come this way, or you just come this way, is absolutely not fixed. It is absolutely not fixed. And hence we face an issue. So that is the biggest drawback of what? One of the biggest drawbacks of what? Linus Pauling and the valence bond theory you must understand. Right? If this is the case, let's go and check another miserable thing where Linus Pauling would not be in a position to explain. You have another drawback. What is the drawback? Observe carefully here. So, the drawbacks of valence bond theory is number one, the projection of p vector or the orbital onto x is not fixed. If it's not fixed, bond angle cannot be fixed. So the shape cannot be determined. You must understand. The shape cannot be determined. That is the biggest drawback. And I propose to you now another drawback. This is another drawback. It is a miserable one. It's really miserable. It's really miserable. It not only fails, but miserably fails. And in fact, I call this to be ridiculous. Except for the concept of overlapping, except for the structures of diatomic molecules beautifully explained, you have all other drawbacks for Linus Pauling and the valence bond theory. And if I can write the ridiculous thing, the second one, it is laughable rather. Second, he says, you look at this, wherever p orbitals are involved, whenever p orbitals are basically what? Involved. Wherever, whatever be the situation, whenever the p orbitals are involved, the bond angle remains to be 90 degrees. Whenever p orbitals are involved, the bond angle remains to be 90 degrees because he thinks that the x, y, z are mutually perpendicular. Since x, y, z are mutually perpendicular, the 2px, 2py, 2pz, whenever they are involved, the bond angle remains to be 90. He is completely shut of the remaining environment, what is happening, the influencing thing, and people approaching one another. Many things happen, and all these he got discounted. He's discounting all other aspects. And just said that whenever p orbitals are involved, the bond angle remains to be 90, which is absolutely ridiculous. It's ridiculous, silly. Now, if this is the case, whenever p orbitals are involved, if the bond angle remains to be 90, in polyatomic system, mind you, bond angles, the discussion of the bond angles will be coming in only when you are discussing basically what a polyatomic molecules, not diatomic. For an angle to be discussed, you should have at least minimum of 3 atoms, right? So otherwise, we are not discussing about the diatomic molecules that are beautifully explained by valence bond theory. Coming into the polyatomic molecules, we have serious drawbacks. They are not silly, they are laughable, ridiculous in fact. One is the projection of the p vector onto S is absolutely not fixed, bond angle not fixed, shapes cannot be determined. The second one is more ridiculous. Whenever p orbitals are involved, the bond angle remains to be 90. So what he is basically telling me that the bond angle of ammonia, PH3, H2O, H2S, ASH3, H2SE, all this bond angle will be 90 degrees. All these bond angles will be 90 degrees. According to Linus Pauling. All. And you know, actually in reality, ammonia bond angle is 107, PH3 is 104, water is 104, H2S is 92, right? And you know, PH3 is also pyramidal, that is around 106. So, you telling me whenever p orbitals are involved, the bond angles remains to be 90 is ridiculous, silly, which we must be in a position to explain. And this is not explained by what? This is not explained by what? Linus Pauling. Now let us take examples and discuss, right, all these things. Observe carefully here. Now whenever p orbitals are involved, bond angles remain to be 90 degrees, which we must be discussing. Right? What we will do is we'll take the case of the fifth group. Take an example of the fifth group. Fifth group hydrides. It's ammonia. You have PH3. You have 3 ASH3. You have SBH3. And 5 you have BiH3. You must understand. You have BiH3. And in all these, the p orbitals are involved. So, according to the VBT bond angle, this must be 90, this must be 90, this must be 90, this must be 90, this must be 90. And at the actual bond angle, if you see actual bond angles, this is 107, this is 106, this is also somewhere like that, and the last one is only 90. So you are tallying only with bismuthine, BiH3, and not the other ones. Right. So, whenever the p orbitals are involved in bonding, the bond angle remains to be 90 is not only laughable, it is ridiculous. It's silly. Now I would like to describe this. Observe carefully. You yourself will be discarding this theory for explaining the bond angles of the polyatomic molecules, and is sticking to only what? Diatomic molecules. Observe carefully, I am explaining. Watch carefully here. Let us take the case of ammonia. Here, the nitrogen is 7 and its configuration is 1s2, 2s2, 2px1, 2py1 and 2pz1. This is the outermost shell. Right? And in ammonia you have two atoms, nitrogen and hydrogen. And the hydrogen will be having the configuration, it is having only one electron, so it is 1s1. Now these p orbitals have unpaired electrons, and Pauling is clearly telling only those electrons which have unpaired electrons shall be participating in bonding. So if I can draw x, y, z, they are mutually perpendicular. This is the y, this is the x, this is the z, and this is the 2px, 2py, and the 2pz. This is the 2px, 2py, 2pz, and you have one electron each. 1, 2, and 3. And they are now at mutually perpendicular. That means the bond angle between x, y, and z is 90 degrees. It is absolutely 90 degrees. Now what you do is the hydrogens, which are 3 in ammonia, this is about nitrogen, this is about nitrogen. Now these hydrogens, which are number 3, you have 3 hydrogens, they approach the nitrogen which are unpaired electrons, and they overlap. This is sp overlap, and it is 1 sigma. So this is how ammonia is formed, 1 sigma. And then you have one more S here, and that's another sigma. This is another sigma, that is NH. And then you have the other one, that is another sigma, that is ammonia. This is how ammonia is, as it is. And you all know X, Y, Z are mutually perpendicular. If X, Y, Z are mutually perpendicular and they are participating in bonding, the bond angle, according to valence bond theory, is 90. It's 90. So the ammonia bond angle must be remaining 90. But you go to the lab, check out the bond angle using an instrumentation available in the lab. Then you will find the actual bond angle 107. Then I dialed Linus Pauling. I called him on his mobile. And I asked him, man, you are telling whenever p orbitals are involved, the bond angle remains to be 90. Well, fine, but the actual bond angle is 107. Could you please explain? Then there is no explanation for this. Hence, I have put it under drawbacks. Under drawbacks. And what is further silly ridiculous is, right below is phosphine, pH 3. And phosphorus is 15. And if I can write the configuration, 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1. The only difference is, this is 2s2, 2px1, 2py1, 2pz1 in what? Nitrogen. And in phosphorus, it is 3s2, 3px1, 3py1, 3pz1. Again, if you go for phosphine structure, this is again X and Y and Z. And this is the 3px, 3py, and the 3pz with 3 electrons here, and the hydrogen comes in overlap, sigma, sigma, sigma. Then I think it's mutually perpendicular, so the bond angle is 90 according to the valence bond theory. But the actual bond angle in phosphine is 106. It's pyramidal in shape. It's 106. How do you explain this? And what is further ridiculous and silly is, if you go down, now this is pH 3, right? If you go down for ASH3, then it will be 4s2, 4px1, 4py1, 4pz1. Again mutually perpendicular. Right? If you go for stibine, that is SPH3, then it will be 5s2, 5px1, 5py1, 5pz1. Again mutually perpendicular. And if you go for bismuthine, BiH3, it is 6s2, 6px1, 6py1, 6pz1. Again mutually perpendicular. So that means he is telling me basically the bond angle of ammonia, the bond angle of phosphine, the bond angle of arsine, the bond angle of stibine, bismuthine, all are equal to 90 degrees, which is not the truth. Not only that, whenever p orbitals are involved, the bond angle remains to be 90. the bond angle remains to be 90 is ridiculous. That means that the entire fifth group hydrides, the bond angle is 90. Will you agree with me? Will you agree with me? No, absolutely not. I can actually give another example. Watch carefully here. Watch. Take the case of sixth group hydrides. Sixth group hydrides. Now what is the sixth group hydrides? Oxygen, sulfur, selenium, tellurium. Right? If you take oxygen, this is water, and the oxygen is 8. So if you write the configuration, 1s2, 2s2, 2px2, 2py1, 2pz1. Here are the unpaired electrons. There are the unpaired electrons. Right? And the hydrogen is having only one electron, that is 1s1. Now remember again, Y and Z are mutually perpendicular. You can see here, Y and Z are mutually perpendicular. Only those electrons which have unpaired electrons will participate in bonding. That was the agreement in what? The valence bond theory. I am not interested in the other people. I am not interested in any of these electrons. Only those electrons which have unpaired electrons I am interested in. So if I can draw the YZ here, the YZ here, it looks like this. Mutually perpendicular. This is the 2py. And this is the 2pz. 2py and 2pz. And you have one electron over here, one electron over here. And you take two hydrogens. I'm discussing water, right? I'm discussing water. You have two hydrogens. One of the hydrogen will come here, one of the hydrogen will come here. It's sp sigma. And this is sp sigma, and the bond angle is 90. The valence bond theory bond angle, the VBT bond angle is basically 90. It's 90. And the actual bond angle (104 degrees 36 minutes). And I called Pauling on his mobile. I was asking him, man, you're telling whenever p orbitals are involved, the bond angle is seem to be 90, but I am actually checking it with the fifth group hydrides and the sixth group hydride. The bond angle is varying, it's not 90, it sounds ridiculous and silly. Could you please explain? And he was not in a position to explain. If he is not in a position to explain, then I put them in drawbacks. You must understand, I need to put them in drawbacks, right? So, let me put it, all these things at one place. Well, all these things at one place, what he means, whenever p orbitals are involved, bond angle remains to be what? 90 degrees. This is what we are explaining. The best way to explain this is take the fifth group hydrides. The VBT bond angle and the actual bond angle. What are the fifth group hydrides? Ammonia, pH3, the valence bond angle is 90, 90, 90, 90 and 90. Actual bond angle differs. It is 107, 106, and it continues to decrease, and the last one is of course what, 90. You might ask me why. Well, that's a separate discussion which we will make it in the coming sessions. So he's asking us to have the same bond angles whenever p orbitals are involved. And similarly, if you wanted to have the sixth group hydrides, that is water, H2S, H2SE, H2T, the valence bond angle is 90, 90, 90, 90. But the real bond angle is somewhere around 104 degrees, 92 degrees, and this corresponds to, of course, what, 90, and the H2T is 90 as predicted by valence bond theory for different reasons, which we will discuss. So, serious, isn't it? It's serious, isn't it? Yes, it is serious. It's not a silly thing. First of all, you said that the biggest drawback is a P projection onto S is absolutely not fixed. Right? So if P projection onto S is not fixed, we'll encounter so many P's overlapping onto S in polyatomic molecules. And if you're not fixing that projection, and the bond angle is not fixed, then the shape is not fixed. So, serious drawbacks. So I would like to list them. Serious drawbacks, in fact, they're not silly, ridiculous. In fact, it is a ridiculous thing. One, projection of P onto S, not fixed. So the projection of P onto S, if it is not fixed, then the bond angle is not fixed. Bond angle is not fixed. Bond angle not fixed. Shape not determined. The best example for this, he cannot explain beryllium chloride. He cannot explain beryllium fluoride. He cannot. He cannot explain this. He cannot explain both these examples. This is the S. This is the P. 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 Now look into this. This can be this way. This can be this way. Which way? Which way? Which way? These are not addressed. They are not addressed. Serious, isn't it not? Because the projection of P onto S is not fixed, then the angle, will it be obtuse? Will it be acute? Will it be perpendicular? Will it be linear? In fact, the beryllium chloride bond angle is 180 degrees. 180 degrees. How do you explain that? No, he cannot. I called him on his mobile. I called him on his mobile to ask him. But he was fumbling, not even fumbling. He says, I don't know. You don't know? Then I put you in drawbacks. These are the drawbacks. Right? Not fixed. So this projection's not fixed. That is the first thing. Right? And now also remember the second one. Whenever p orbitals involved, whenever p orbitals are involved, bond angle remains to be 90 degrees. Whenever p orbitals are involved, the bond angle remains to be what? 90 degrees. It's ridiculous. For example, according to VBT, bond angles of all hydrides of the 5th group and the 6th group remain 90 degrees, which is not the case. Which is not the case. If it's not the case, you ask him, call him on his mobile. You ask him why. He is not explaining. So what has basically happened is, except for his overlapping concept, he is not looking at the surroundings, what's happening. Because it's not as simple, well, I'm here, some people are approaching me for bonding, I'm an atom, and the other atoms are approaching me for bonding, right? So without any preparation, I get into excited state. I don't sit in any positions. You just ask these fellows to come and overlap is something which we must be thinking of. The other thing also what we should think is when two atoms are approaching each other, every orbital in that atom gets influenced. Every atom in that gets what? Influenced. Sorry, every orbital in an atom gets influenced. But we are only considering the outermost subshells. So the major issues why such drawbacks are arising is basically, except for overlappings of atomic orbitals, we have discounted everything. We have discounted everything. The P is projecting onto S, you have a sigma bond. The P is projecting onto P, you have a sigma bond. If it is a sidewise overlap, you have a pi bond. We are not considering anything, our environment, what's happening in the environment during the bond formation. So this fellow's theory is basically restricted to diatomic molecules, beautifully explained. Except for that, everything is a demerit for them. Yes, one thing will be carried forward, that is the concept of overlapping. Only through the concept of overlapping, you can explain the strength of the covalent bond, where is it derived from? Unless you introduce the concept of overlapping, and unless the energy is released, stability cannot be explained. So only thing now from this session, what I'm taking in my pocket and going out, is basically what I'm taking and going out is the concept of what? Overlapping, which is carried forward till date, and it will be carried forward even in future.